So of a circle. So this is 3.8 continues.
Literally, I would like die if I tried to do that.
Which one do you?
Yeah.
Yeah, well.
So you just, if you remember Papa's, it's not too bad, right?
Yes.
You have like A,
Oh, what did you
It was
C,
good.
E.
I don't think that's how it works, man.
I knew it off the top of my
No, you did not.
See, it's this one. If A, C, and E are 3 points, then
On line B, D, F.
no.
And 3 lines A, B, C, D, E, F, B, D, F, A, B, C, respectively.
Alright, guys.
3 points in this section.
I know you're excited. It's been a long time.
Approximately 1 week.
Approximately.
Blaze Pascal. Wait, is this the same guy that made the Pascal triangle?
What do you think?
Probably.
Probably. I'm pretty sure it is. Yeah, it is not Blaise. The other guy was also Blaise Pascal. Unless there's just 2 Blaise Pascals.
Another one.
Another one. Another Leonie.
But maybe the Pascal's triangle is this guy. Because this guy did this when he was 16 apparently, right?
What?
Or maybe his
Wait,
son's
that
name is Blaise Pascal.
You didn't even let us sink in, and then he's like, come up with an inferior idea and say it.
No, it's superior.
Nice.
Maybe his son's name is Blaise Pascal. And his son's name is Blaise Pascal.
Okay, so this point, I'll label the points in a different color, just for your convenience.
Yeah.
Okay, so that's a U, yeah?
That's pretty bad.
E, C. Remember how this works?
Yes.
It's like it's like the hexagon, right? A, E, C, D, E, F. Yeah?
Sky is king.
It's a
Oh, this feels so much better.
Yeah, so there's many ways that this can be inscribed in a circle, hexagons, yeah? So what's the claim? If all the vertices on a hexagon lie on a circle, the 3 pairs of opposite sides intersect, and if they lie on a circle and the 3 pairs of opposite sides intersect, then the 3 points of intersection are collinear. Yeah.
yeah.
So remember, what are the points of intersection here? What are the opposite sides? So if you look at just like a normal hexagon, right?
That's not
That's not
Convex hexagon, yeah.
Yes.
What are the opposite sides?
F, C, E, B, A, D.
What's that?
D, A, B, yeah.
Yes.
So that's like this point here.
Opposite sides, not opposite points.
True.
Yeah.
D, E, A, B.
And
C,
then
B,
B, C,
F, E.
B, C, F, E, yeah.
Yes.
So B, C,
That does not.
That one.
F, E, yeah.
And then D, C, F, A.
D, C, F, A. Yeah, right?
Yes.
So that's saying these are collinear.
Whoa. We did it.
We finished.
It's like this is a
Yes.
counter example.
Oh. Yes, we've unproved it.
Okay.
Just do it like extremely accurate and find a camera example.
The reader can easily.
Yeah, because.
So the reader can easily see. It says.
You're so blind.
Yeah, what modifications in the argument will be needed if the arrangement is different? Yeah, so I guess, we can draw many different hexagons. It's more important, as I keep saying, to be aware of the different possibilities. And because that's usually the harder one. Okay? And then actually dealing with them usually uses the same ideas as the original. Alright guys, focus.
See this.
So These are 3 questions.
That's a lot.
Here's 3.
Okay, so
Plus A, B, D.
so we wish to prove that these 3 points are collinear, yeah? Any ideas? So I think in other circumstances I could keep reading, but for you guys, you should probably have some idea what we're going to do. Or something to try. Any ideas?
Similar triangle.
No, they're no.
Like that. The intersection of the middle one, C, and the one on the left.
Mm-hmm. Yeah,
So
so there's
label
some
that
similar
point?
triangles that might help us, yeah.
Can you label that point?
Which one?
That one with E and C. Yeah.
This one, yeah?
Yeah.
Okay, that's a good idea.
Oh, like
Maybe-
E, C, X, B, E, X, D. Which
So-
ones are similar?
The EC,
And then this tiny one and the big one with C in it.
Like the flipped one.
The big one with C in it. See this one?
like this one
That's-
here, yeah? That one, yeah?
Yeah.
What X?
Yes. So then left point.
Do you want me to label
X.
all these other points?
Yeah.
Elementary.
Element, literally just use the one in the book.
Yeah, element.
And then so LX.
Oh, so this is LMN, yeah?
Yeah.
Oh.
Are you sure this similar?
And then NCN.
N, C, L. Wait. Huh? L.
LXN and MCN.
What? How do you think this is similar? You can do like XL parallel to CT, but that's not true, so. I'm pretty sure they're not. They don't have to be similar. Yeah, they don't have to be
No,
similar.
I mean I don't know.
Alright, so I mean, does it remind you of something we did before?
The one with straight lines.
Yeah, the one where AC was a straight line, right?
But it's not a straight line.
It's not a straight line, so that exact proof won't work, right?
Ah, modified version. Yes. Wait, what was that proof?
What was that theorem?
We just read it like 1 minute ago. Come on.
What that one? No, we didn't.
Yeah, that was practice.
Oh!
Ah, Pappus's theorem, yeah?
We talked about
Propose.
Oh, it was a weird, I don't know, where we just multiplied lots of stuff and then
Why?
we divided lots of stuff. I think.
Go ahead, write that proof right now. Without looking at the book.
Oh, so this theorem is different.
It is this theorem.
What?
That theorem is this theorem.
No, they're different.
Then go write proof of this theorem.
I just copy what it says.
No,
Yeah.
without looking at the book.
The projected
Without looking at the
data.
book.
I'll keep it on.
Unlucky Leo. Okay, this is kind of the same. Except now we just have a circle.
So do
We
you
have
remember?
extra info.
So do you remember what we did last time was Menelaus, right? So I mean, it doesn't mean it's the only way, but if some problems are already being solved and you know about it, and this problem is similar, that's probably the easiest way, right?
Probably.
Wait, this literally has the same points.
Like, what was Menelaus?
So remember Menelaus was saying that if you have these things times together to 1 or minus 1, then it's
Yeah.
collinear, right? So that's what we're looking for, yeah? For the Pappus's
That's
theorem.
not similar triangles. Because then you could, like, nah. I don't know.
So you don't even listen to what I'm saying,
Okay,
yeah? And yeah. So we have these collinear points, right? The same as we did in the Pappus's theorem. The only thing we don't have is the ACE in the BDF, right?
Yeah.
So we're missing 2 equations. Does that make sense?
Yeah.
Can we make a point lower than C on AE?
But that would make like loads more points. Like a lot. Because you'd have to link it to B, D, and F again.
Yeah, so I guess what triangle could we use? So we want to show N, L, and M are collinear, right?
Yeah.
So what triangle could we use for that?
C and M.
C and M. No, do we ever use a vertex of the triangle?
No.
No,
You use
that one.
what?
The E.
U. Yes. U.
Yes, U.
UDF.
UDF, yeah.
Yes. Or UEC.
Hey,
Oh.
UDF and UEC. Wait, is EC and DF?
UEC?
Yeah, and U or UDF.
Oh yeah, U should probably be in red, huh?
Wait,
Hmm.
also UEC and UDF.
Are they now?
Yeah.
Are you sure, Kamal?
The extended lines.
Are you
Are
sure,
they?
Kamal?
Wait, am I sure? I don't know. No, I'm not sure.
Are you sure? Come on.
I actually don't know anymore. No, I'm not sure. No, it's fine. Erase that thought.
Menelates. Difference.
Yeah, do you remember how Menelaus worked?
Yes.
Look at that.
Times lots of sides together.
Yes,
And
the
if
word.
it equals 1, they're collinear.
So it's like this, you have like this triangle, right? ABC. Yeah?
So you just times two of those and get.
So one of the points that you get collinear is the extension of one of the sides of the triangle, yeah?
Mm-hmm.
Actually, they're the extensions of the sides of the triangle, all of them. You see that?
Oh, wait. Then you can't use that. Yeah.
You can use.
So whatever triangle you pick, it has to have these 3 points on the extension of
Yeah.
the side, right?
C on
This is very difficult.
C and M. Again.
C.
What?
How are you meant to pick?
There's like, I don't see a point that goes to both. Oh, wait, no. I don't see a point that goes to both. Well, I just
This is a command.
that Leo is also experiencing.
Oh, I know. You.
Yeah,
Wait,
kind of.
what? No. UVA. Wait, what? No. U.
PA. No.
Wait.
Yeah, that's a good idea. Yeah, what else? UV what?
UVW.
Yeah, UVW.
Ah, I did it.
Yeah, UVW, that's good. So what would be the kind of thing you want to show, right? So, do you remember what the theorem actually says?
dx over cx times cy over ay times az over bz equals 1. Wow, I'm good at reading. You see?
Yeah, but wait, we want UW and V.
Yes, just replace A, B, C. Wait, no, you have to replace everything.
So there's like,
U. X is on B and C, so UN times NV. UN over NV. UN over VN
And how we have U
times
and W.
VL over.
Sorry.
so you're saying, I'll write down what you're saying. UN
Over VN
VN
times VL over L WL,
L over WL.
and then dog times W M,
M.
yes, over UM.
This seems kind of right. And what should it equal to?
1
1.
or negative 1.
I think it should be 1 if the ends are lined up. Yeah.
Yeah, but UM
You can check it for yourself.
negative.
Yeah, it's a big bang.
Wait, isn't it negative 1?
So UN, VN. Okay, that's negative.
Negative 1.
VL and WL.
Yeah, it's negative, I think.
Okay.
Wait, actually, no.
WM.
Oh no, it is. Because like going clockwise is like positive.
Going anti is negative.
Oh,
Yeah, I
but
think it's positive.
hold on, but WM on UM.
Oh yeah, that's still positive. Yeah, so it's positive 1.
Yeah.
Positive 1.
Positivity.
Okay, does that make sense? It does. We have to show that this is equal to 1. Yeah.
Yes.
That's what we have to show. Okay. What kind of stuff do we have?
Why is M on that triangle again?
Because it's on UW extended.
Okay, so let's look at things like LDE. Yeah. LDE. Yeah.
Yes.
Okay, so what's LDE? So what's LDE being collinear mean? What triangle can we use?
LDE.
DLW. Yeah. Oh, DEU.
Yeah, DEU. Yep.
Are we doing LD?
LD and then on LE and then no. Can you?
Hold on. D.
Hold
Can you use the same points that you're trying to? Does that work? No, that would make it equal 0.
on. Yeah.
ELD.
Literally.
What? You can't use the points you're trying to. No, it doesn't work.
So LDE, what triangle can we put them on?
LD.
You have to use all 3.
Yeah. Well, what? No.
No.
Oh, yeah.
There's only DEU, DEC. DEC doesn't work. Does he not work?
U and M. Yeah, U and M.
U. What?
U and M.
And M.
Yes, that works, right?
That triangle.
Yeah.
And it's literally this diagram.
Because it gives you.
Oh yeah, that does
And then
work.
it does this.
That's pretty epic.
That's pretty menelaus.
You're mental. U and M.
You wanna
I'm the moon.
1, 2,
U and M.
Eminem is even.
Yeah, I wonder if it matters if we use a different ones what they use. So if we do U and M.
Wait, did they use
What
a
did they
different
use?
one?
Yeah.
They use UEC. Wait, no.
Easy.
That's the one. What else can we use? What did they use? Did they use UVW. Yeah, you can use UVW or
UVW.
like the same one that we used for the other one.
Yeah. I guess which one would you choose if you could choose?
The same. Wait. With you?
Like if you can do it for the same actual triangle, yeah?
Yeah, then if we use both at the same time.
That'd be nice, wouldn't it?
Yes.
So let's do the same. So the same triangle, UVW, isn't it?
Yeah.
So UVW, yeah. And then VWU. What is it?
UVW. Oh. E. It's just like
It's not.
UV.
Do it.
What? Isn't it like EELLDD?
E. And then
No,
VW.
L.
Wait, yeah, LL.
DD.
Yes.
And then what would you get? 1 or minus 1?
VE times VE minus 1 VL WL WD positive 1. Yes, positive 1.
Yeah, so that's what they got, but in a different order, yeah.
Oh,
Okay, so that could help. So we don't actually have exactly what we need yet, right? We have VL and WL. That's one thing we have, right? Remember how last time we did it, we got one useful kind of fraction out of every one we got. So that one's VL and WL, yeah?
Oh, yeah. Oh, do we have to find more?
Yeah.
Oh,
So that means you should get
VL.
3, right? There should be
Yes.
3.
Then we do VL later and then. Wait. But actually,
So this is...
we can do VL later.
Seems like you use the same triangle again, hopefully, right?
Probably.
UVW, and now you can do some other collinear lines, like maybe ALDB, right?
ALB. Does that?
Right.
I think
Can you do
that.
AMF?
So we have UVW, yeah?
UV.
Oh, yeah, I guess if you use A or B, then...
I don't think that works if you use the same triangle.
Yeah, because if you can't use A or B, right?
Yeah.
But we could use F with A. Hold on, so UVW, right?
Yeah.
You can do
Oh, you can do, yeah, AMF, because one was correct.
AMF.
Yeah.
Yeah?
Yes, that was Kavan's idea.
Thank you, Kavan.
Good job, Kavan.
Let's do it again, okay? So UVW, yeah?
Yes.
VW. U, yeah?
Yes.
And where does the AMF go?
It's FFNMA.
F,
Genius.
F,
M,
A.
A. So okay, let's see, it was...
So
Equals.
V. Wait, no.
Equals.
What's the
1.
same? Literally nothing is the same.
Yeah.
We have WM on U. No, that's not even the same.
Wait.
Wait a minute, where's M? It should be A, right? VW should be A.
Oh yeah, oops, we did it wrong.
This is A, yeah?
Yeah.
And the
then
other
it's
one's
M.
fan.
Oh.
W, M, U, M.
And that's the last one. So that third one's the same thing.
Yes.
Well, not the same.
The third one.
Important.
That's 1, yeah?
Yes, another one.
The
Yeah, WMUM is
WMUM is the same as one.
W, M, U, M. Yeah, I mean, it's a good thing that it is, right?
Yes, it is.
So that's what we're going
The
for.
third one being the same.
How do you do the third one?
I do not know.
Probably the same triangle again, right?
Yeah.
Because we need this one now, right? U and V.
U, V.
And then we need an N, yeah?
Are they
So
even any?
U and V.
V, and then N, yeah?
So then, what about UVA? No, that doesn't work.
It should be the same triangle, yeah?
Yeah, U, V, W.
How about B,
B
B,
and C.
B and C.
B, and C?
I
Yeah.
think so. Yeah.
Wait.
Wait. Yeah, because
Yeah,
it
no,
uses
no.
N again.
Yeah.
Yeah.
Okay, this is the epic.
Oh, so it's looking good, yeah?
B and C.
Yeah, W, A. Yeah, it's matching what the book says at the moment, okay?
Yeah.
Which isn't, it's not the ultimate authority, but it does help to
It just tells us that we have
Not
done.
horribly wrong.
We're not horribly wrong. We may be wrong, but not horribly wrong, because the book can be wrong. Sure.
Yes. So,
Okay, so where are we at here?
Again, V and V W.
Okay, and then we've got the N we need, right?
Yeah.
What else?
V.
CB? CCBD? Or am I being high?
C.
Yeah, I think
I think it's CCBD.
V W. Yeah.
Yeah.
Wait. No.
Is it?
BBC.
No, BBCC, sorry. I'm being high. Yes.
So B.
And then CC.
Oh, very interesting. Please.
The B's were originally C, so this is what happens when you change stuff.
Oh gee.
Oh,
We got all three.
now I have to go in.
With
Now-
their cameras.
and the others.
Okay.
That means that the other two times to 6. Times to 1.
Yeah, so basically, if you times them together, right?
So literally,
For that to be 1, all the other stuff has to be 1, right?
Yeah.
or they could be 0.
Both.
Okay, so I think it's good to try to understand it, because if you just read it, it's too easy to check it, right? You don't really know what the problem is, yeah? So remember, what we did last time, we had this exact same thing from before, right?
Yeah.
Exact same thing. How do we make the other stuff times the other 1, remember?
How did we?
Do we use different triangles?
Well, I mean, there's 2 Menelaus missing, right? Remember? There's 2, 3, 6 other fractions, yeah?
Yeah.
It's 2 Menelaus. That comes from the collinearity of ACE and DFP,
Because we
yeah?
just done.
Remember?
We've only used V.
Oh yeah.
So that doesn't happen anymore, right?
Oh no.
So now we're not on our own, I guess, but can you not lean on it, please? Oh, good. Yeah. So I don't really care about the wall. I just want to exert my power over you. Right.
Lucky boy.
Yeah. So, no, I do care about the wall too.
Pat. It's okay, Wall.
Okay, so we need some other way to get all the other stuff. We go to 1, right?
Use
Yeah.
other lines. And
So
do
we have
it
like
again.
U, E.
Whoa. But they're not straight lines anymore.
The other ones.
Yeah. Because we're left with A, B, C, D, E, F, and they're all in a hexagon. So you can't make.
Hey.
So W, but remember the difference is on a circle, right?
Yeah.
So
Yeah.
if this is actually a circle theorem, you have to use the fact that on a circle to do something, yeah.
Hmm.
Sorry. Wait, what is a cyclic hexagon?
Hmm.
Like, what's the definition again?
They lie on a circle.
No, but what's the angle? Like,
Well, it doesn't have to have like
so it
some
doesn't have an
angle
opposite thing,
requirement.
right? Yeah, okay, good.
What?
Because I was like so confused last time about that. I'm like, what's the angle for this?
Because it changes. Like you just move on.
You
Like,
get, that's what I was thinking. I'm like, how does this even work? You just change this one, the opposite one doesn't change.
this is a command mode.
Yes. Okay, good. Well, now that we've got that clear, time
So
to
what
go back to work.
what can we do?
What can we do?
But what can we do?
Oh, how does it being in a circle interesting? Any ideas?
We
Leo might have an excuse depending on if he's done this, but you have less of an excuse.
Yes.
did
Wow.
into the quadrant.
What? Quadrant.
Okay, what happened? What this does this jog a memory? Like what's like UC times UT?
You see. Oh, the power of a point.
Oh,
Ah, see, you have. There is no excuse. Come on.
okay. So there's lots of powers here, right? Can you see that? So when you times them all together, you get a UC times a UT, right?
Yeah. Yeah.
No?
Which equals UE times
Take off.
Yeah.
Yeah.
Which equals what? Which equals what? What did you say?
UE times UF.
Yeah.
Ah, but do you see a UE times UF is on the numerator now, right?
Oh, gee, and they
Gee, and
cancel
they
out.
cancel.
Whoa.
So UE UF, right?
Yeah.
With UC
UC,
UT.
D,
Yes.
and then
Wait. V. Oh, there's. Okay.
VE,
Then you use it on V.
VE.
So then VB times VA
VB, and V. Yeah.
equals to VF times VE.
VE.
So V.
Wait, no.
Wait.
Yeah, E, same thing. That's what I meant.
Huh?
Yeah.
It is V.
Yeah, I know.
Yeah.
I said
So
V.
VB and VA. You have to check that on top, yeah? They're both on top, yeah?
Yeah.
And then what do they cancel with?
VE on VF.
Yes,
V.
it works.
VF, yeah?
And
Cancel,
you
cancel.
use WC,
WC and
WD,
WD.
and then WA, WV.
High five.
Oh, good job, come on.
So let's see, W's, what are the
WC.
power of W, is that what you're saying?
Yeah.
WC,
WD.
WD, yeah?
And then WA,
WA,
WV.
WB.
WA, will be, yeah?
We did it. OMG.
Got rid of the six fraction.
Yeah, that's pretty cool, huh?
This is so cool.
Yeah. That's called Pascal's triangle. Pascal's theorem. Pascal.
Pascal's.
Wait, so Pascal's triangle came after Pascal's hexagon.
Yeah. I mean, he probably
He
just half.
downgraded
No, he
the
just halved it.
What?
He just half. Because hexagons equal to two triangles. So he just
Wow.
he just made two triangles out of the theorem.
Sure.
Wall.
Yeah,
It's on the wall though.
Stop breaking the wall, come on. Oh, come on.
I am still very confused.
Okay. So therefore it's collinear, right?
Yes.
Says this attempt to reconstruct Pascal's proof appeared in the 18th edition of Theodore Speaker's Le Bouc de Iberian Geometry, Potsdam in 1888.
Or
Oh, okay, so I guess he mentions some different references. Oh, and the authors of the book also has an article on it, like the Hexagram de Pascal, un essai pour reconstituer. Oh, so it's French. In 1963, okay? Yeah. Cool. In a circle, wait, so what does it say? In a circle, but equally well inscribed in it. Oh. Okay, so there's some actual comments after this line as well. So the line containing the 3 points LMN, yeah, is called the Pascal line
whoa, Pascal.
of the hexagon, So this is kind of it'll get annoying when you read people's solutions to things and like, let this be the Pascal line and you have no idea what's going on. But now you're like on the other side of that.
Pascal. Wow.
Okay, I have a hexagon A, B, C, D, E, F. As we saw in section 3.7, the same 6 points determine 60 hexagons. Consequently, they determine, in general, 60 Pascal lines. These 60 lines form a very interesting configuration. Certain sets of them are concurrent. Certain sets of the points of concurrence are collinear, and so on. Well, that's kind of interesting. You know what I'm talking about?
Yeah.
If you made all these other hexagons and made these other lines, they have interesting configurations.
Well, you can make 60 that could be.
According to a brief essay, Pour les coniques, which has survived, Pascal was well aware of this theorem, that his theorem applies not only to a hexagon inscribed in a circle, but equally well to a hexagon inscribed in a conic. Oh, okay, so a conic.
Is that like oval?
Yeah, so we'll have a different definition in this book, but from school, that used to be in the school syllabus.
Oh.
I mean, just generally, it's called a conic because you can get a cone, right? And you can cut it, and the shapes that you get as the cross sections are conics. So if you cut it horizontally, you get a circle, right?
Yeah.
If you cut it like sideways, you get an ellipse. If you cut it like sort of vertically, you get like a parabola or hyperbola. That kind of stuff, yeah.
Yeah, it's kind of
like you cut like the corner of it off, you know.
Oh.
Yeah, like
this.
if you had a
It's
not the point, yeah, but like something on the.
You just get like this. Cut it on the side like this.
The converse theorem, proved independently by William Breckenridge and Colin McLaurin, can be found in textbooks on projective geometry. Okay, if the three pairs. Oh, so this is an example. If the three pairs of opposite sides of a hexagon meet at 3 collinear points, then the 6 vertices lie on a conic, which may degenerate into a pair of lines.
Degenerate.
Oh, okay.
Degenerate.
What does it mean to degenerate into a pair of lines, by the way?
Wait. That's a degenerate hexagon. Oh, like when the points coincide.
Yeah, so can you, like, is it obvious that the converse of this theorem is not true, right?
Yeah, because it can be a straight line.
It could be a straight line and they don't lie on a circle, right? Mm-hmm. Yeah, but the way they had the converse, they replaced circle with conic.
Literally,
and then the conic sort of if they consider the degeneracies into lines, they consider all those cases at once and then have a converse. Yeah.
And if it's a straight line, you can literally just prove. I mean, that.
Okay, so this next part.
And it doesn't lie on
it says.
It's true.
By permitting vertices of the inscribed hexagon to coalesce, okay, and labeling them carefully,
Coalesce?
we can deduce. Illiterate. Coalesce.
What does that mean?
Like, come together.
Converge?
Yeah, well, converge.
Not sciencey. Okay, so coalesce is like the mathsy version of converge.
No, converge is probably the most mathsy word there is.
What?
Yeah, you only use like when do you
coalesce is like celestial.
Begin.
Alright, yeah, by permitting vertices of the inscribed hexagon to coalesce and labeling them carefully, we can deduce some interesting theorems concerning inscribed pentagons and quadrangles. So this is what we were talking about last time. Yeah. You know how you said you missed pentagons?
Oh yeah.
It's like
we directly went on to hexagons.
Yeah.
How's that?
It's like once I know you long enough, I can just kind of simulate your lives in my brain.
What?
Okay, so in such cases, the side whose endpoints are made to coincide becomes a point. But the line containing it becomes a tangent to the circle. Or conic at that point. Consider, for instance, the inscribed quadrangle ABDE shown in figure 3.8b. Okay, let's draw their figure now, okay?
ABD is a degenerate hexagon.
You're a degenerate.
You're a degenerate.
Oh.
Oh, let's see.
Oh, I haven't done my science homework.
I haven't done my science homework.
It's due
And
tomorrow.
it's due 2 days ago.
Wait, no, it's due today. Wait.
Wait, is
And
it
then-
style?
And it's,
No,
you're
it's
doing an
online.
experiment on what happens if you don't do your science homework.
Ah, yes.
Hmm.
Of course.
If
Okay,
you don't do your
so-
science homework for 1 day, if you don't do your science homework for 3 days. Sure.
So this is the figure that's drawn, okay? Circle. A. A. D. Is that an E? B. M, yeah?
Yeah.
So I guess this is trying to say that C was and B and F, they just coincided with. So maybe I should have kept the other diagram up, but maybe. So originally, remember we had all these other stuff. A, B, C, D, E, F.
Yes. Very interesting.
Yeah?
What happens when you address the star?
My star is very good.
Why do you have 2 E's?
No, I don't have ball drop 2 E's. That's a D. Okay. So maybe not quite. So I guess that's like flipped. So the A's are on the right and there's A's on the left, yeah? And then
Show me back.
P and F come together.
Let's see. What? I have left this out.
What did the word?
E and F come together. B and C come together.
Yeah. Wait.
Yeah, maybe it was better that we didn't draw the diagram, huh?
Hmm.
E and F come together. And B and C come together. It's weird because they're like crossing each other, huh?
Yeah.
Okay, let's see what they make of it anyway. So you have this line. This line. And the tangent at E. The tangent at B. Maybe I'll draw the tangents in blue. And that's N. And that's L. And that's M. Yeah.
Yeah.
And is there another tangent? That's it, there's no more tangents, right?
Mm-hmm.
Okay, so what happens? So by permitting the vertices to coalesce, labeling them carefully, we can deduce some interesting theorems about pentagons and quadrangles. In such cases, the sides whose endpoints are made to coincide becomes a point, but the line... Oh, okay. So even though they're crossing each other, B and C is the side of the hexagon, right? That's why they're coming together.
Oh.
So you're making the length 0, yeah?
Yes.
And E and F are a side, yeah? Okay, that's good. Mm-hmm. But the line containing it becomes a content. So consider, for instance, inscribed quadrangle ADBE, okay? So that's ADBE, yeah?
Mm-hmm.
shown in the figure. By regarding the cross quadrangle ABTE as a degenerate hexagon with B equals C, E equals F, right? We can apply Pascal's theorem with the conclusion that the tangents at B and E meet at N, and LM and N are collinear.
Yeah.
Yeah? So remember what it was, okay? If this was a hexagon, yeah? Then opposite sides are the ones that make the intersections, yeah?
Yeah.
So L was, remember which... So it was
Yeah.
like
A, B,
C, D, E, F, right? A, B, D, E.
Yes.
They're giving you one of them. So that's L, right?
Yeah.
And then E, so B, C, E, F, yeah? So EF is now a tangent, yeah?
Oh yeah.
BC is now a tangent, and they now meet at N, yeah? Okay?
Yeah. And then A, B, wait, no. A, F, C, D. A, F, C, D.
Yeah. And then A, F, C, D, yeah? That's M. Yes, so for a cyclic quad, right?
Yeah.
You get that.
Oh, you be to the.
Yeah. So this is kind of like if you did like the cyclic quad version of that. Yeah.
Wait, why does it have to be a tangent? Like, if EF was like.
Oh, I mean, if E and F collapse, right?
Yeah.
Like normally it'd be the extension of the sides, right?
Yeah. Oh, okay, yeah. So it moves across the circle until.
Yeah.
Okay. Wait, what if you thought about it like where it was like the ACE was like still the straight line, and then you moved C. Like actually, I don't think that works. Yeah, that one actually.
Oh, you mean do a degenerate version of the other theorem?
Yeah, two straight lines instead. Well, no, wait, that wouldn't work though, because then you'd be proving it for any quadrilateral.
Yeah, that's pretty cool, right? So now it's not a hexagon, right? And a lot of there's a lot of problems that you see, like they end up just being sort of a degenerate version of like a famous theorem or something.
Oh.
And if you kind of so I think this tells you that. I guess what this tells you is like if you saw this, right, I think you should be able to prove it directly with Menelaus and PowerPoint.
Yeah.
Does that make sense? And it's a very nice observation to relate it as a degeneracy of Pascal's theorem, right?
Yeah.
So depending on who your audience is, I guess, you convince them differently, right? Like if you're someone who knows this, you're like, oh, that's just Pascal's theorem, and they're just like, wow.
Oh.
So you sometimes have to show them how it's that, right? But if they didn't know Pascal's theorem, well, you could use your knowledge of Pascal's theorem and just do the proof with Menelaus and PowerPoint. Yeah? And then it might simplify quite a lot. Yeah? Or there might even be, okay, and then obviously because that covers all the cases, it might not cover the special one really well, right? So there might be even simpler proof that goes straight to the point.
Yeah.
In this case, yeah?